Titration of a strong acid with a strong base. What is the pH at the equivalence point for the titration of any concentration of strong acid with any concentration of strong base? It's going to be a pH equal to 7. At the equivalence point, the strong acid and strong base have been neutralized, resulting in a salt that is a neutral salt, creating a neutral solution, and that's a pH 7. So we know that if we have a salt that has parents that are both strong, a strong acid and strong base parent, then we're going to create a solution that is neutral with that salt. So there's no point in saying what is the pH at the equivalence point for a strong acid, strong base. It's always 7. That's not true for the other two possibilities we're going to work with. But so what we normally do with a strong acid and strong base is that we either under or over titrate the solution, so that we have an excess of acid or an excess of base. So it's, instead of saying what's the pH at the equivalence point, we're saying what is it before we reach it, or what is it afterwards. So take a look here. We have 50 mils of 0.1 molar HCl and 30 mils of 0.1 molar sodium hydroxide. So you can see that we have more at the same concentration. We have more acid than base. So we should all the base should be used up and leave only behind the acid. So since we're titrating, we're mixing, so we're going to have to convert to moles. So let's do that now. We have 0.0. So when you have a strong acid and a strong base, what you want to do, I'm not going to give you it at equivalence point. I might ask you that question because it's going to be pH 7. So that's easy, but I'm going to give you two solutions that have different amounts of moles of HCl and NaOH so that they don't balance out. They don't neutralize each other. There's going to be one that's left in excess. Figure out what that is, get the concentration, and it's going to be either acid that's left over and then convert directly to pH, or it's going to be OH minus that's left over, convert to POH and then to pH. And that's what I'm asking for here, is the pH. So this is 0.00300 moles of sodium hydroxide. Now, HCl plus sodium hydroxide go to water and sodium chloride. So when we, I guess we could do it as an ice table, why not? We have 0.00500, 0.00300. Oh, we don't have a 0 there. Then we're going to lose all of the sodium hydroxide. We're going to produce a certain number of moles of the sodium, same number of moles of sodium chloride. We're down to this much HCl, 0, and we don't care about the salt. It's going to be neutral, but what we do have is 0.00200 moles of HCl over the new volume, which is 0.0800 liters. We have 50 and 30, so that's 80 mils, or 0.0800 liters, and that comes up to be 0.0. Now that acid, HCl in water, produces H3O plus and Cl minus, and it's 100% dissociation. So I'm not going to put an ice table here. You could, but 0.025 molar HCl produces 0.025 molar H3O plus. So the pH is going to be the negative log of the concentration of H3O plus, and so we get a pH of 1.60. So what we do is we determine the number of moles of strong acid, strong base, figure out which one runs out first, and how much of the other one is left over. In this case, it was the acid. So we then figure out how many moles of the acid we have, convert to concentration, and then convert that concentration of acid over to concentration of H3O+, and find the pH. So that was a fairly easy one. This one's a little trickier. We have to be a little bit careful. What is the pH of 40 mils of 0.25 molar nitric acid that has been titrated with 25 mils of 0.3 molar calcium hydroxide? There's 2 OH minuses present in this calcium hydroxide. So we got to be careful here. Let's convert to moles. This comes up to be 0.0100 moles of HNO3, and then it's 0.025 liters of calcium hydroxide. Gives us 0.0075 moles of calcium hydroxide. Now, to save us a little trouble, the calcium does nothing for us. Now the calcium hydroxide breaks up into calcium ion that goes away, doesn't do anything for us, and then 2 OH minus. So for every mole of calcium hydroxide, we get 2 moles of OH minus. So if we have 0.0075 moles of calcium hydroxide, we have 0.0150 moles of OH minus. And I do this out because the OH minus is what's going to react with the acid. It's just easier to deal with than to have that calcium, to drag that calcium all the way along. But what happens here, we have HNO3 plus the OH minus will react 100% with each other till one of them runs out. We'll get water, and then we'll get the nitrate ion. And you say, well, what if we kept the calcium hydroxide? You can, you just got to be really careful, because then it's going to be 2 HNO3 to 1 calcium hydroxide. It's better to just get it into this form. That's as tough as it's going to get, but calcium hydroxide is a strong base, so we need to be able to work with that. And you can try it the other way. You can try it just like I did it previously. Whoops, this is with that last one, and it will work out. You just have a little more work to do. It's better to convert to just OH minus and be done. This is 0. So now this time it's the acid that runs out first. And then this is plus. And you notice that sometimes I put the units in, maybe just at the top, sometimes I carry them through. Just depends on how much room I have. But if I don't carry them all the way through, or I only put them at the end, it's because we know what they are. And it doesn't hurt anything to not have them in our ice table. It's generally at the end that you need to keep track of the units, as long as we know what they are. Now we have 0.00500 moles of OH minus, and then the nitrate we don't care about. So the concentration of OH minus is going to be the moles divided by our new volume, which was 65 mils, 40 plus 25. And this comes up to be 0.0769 molar, and the pH is going to be 12.9. This is the concentration of OH minus, and then we convert to POH and then to pH. I think that's where we're going to stop.